So we have an idea what vectors are, so let's talk about adding vectors. So first of all, I'm going to do colinear vectors. This is one-dimensional vectors. Let's start with that easy, then we'll go to two-dimensional vectors. So with one-dimensional vectors, let's say that we have 6 feet to the east. Okay, and let's say that's a vector. To symbolize what a vector is, I'm going to use A as my variable, and I put a little arrow on top of it, indicate it's a vector. And I'm going to say vector B is going to be 3 feet east. Okay, and so I want to know what is the result of adding A plus B. Okay, and so there's several ways of doing this. You just look at it and say, well gosh, 6 feet east, 3 feet east, that's 9 feet east. Okay. You can do this graphically too, and I'll have a whole presentation about graphical adding of vectors. But what you can do is, and it's very helpful, is you have an origin here, and you say vector A here, and you draw vector A, and you go 6 feet to the east. Now, you don't literally have to go 6 feet. If you have a piece of graph paper, it's not going to be 6 feet long, but you could actually do this so that you draw it to scale and say, well, every half inch represents a foot, and so 6 feet would be 3 inches. So you draw it 3 feet, the 3 inches, and that represents 6 feet. And then 3 feet would be 1.5 inches. You draw 1.5 inches. Now what you do is this is an operator. So that means you do this, then you do that. So where the first one ends up, we draw vector B. Okay, vector R is the result of this. So it goes from the very beginning of the first all the way out here to the very end of the second. So that's going to be vector R. It's the result of adding vector A and vector B. And so that's going to be this. Now, what if we had B plus A? So remember, B is 3 feet east, and A is 6 feet east. So what happens here? Well, what we do is we go 3 feet to the east, that's vector B. When we end, we then go 6 feet to the east, that's vector A. The result is from the very beginning to the very end, and once again, the result vector is going to be 9 feet to the east. Okay. The vector is always, you can't just say 9 feet, you got to say 9 feet in what direction. And so you always have to give a direction to this. Otherwise, it's not a vector. 9 feet to the east. Okay. Now we would also, just as I'm mentioning this, the result vector there was 9 feet to the east. Okay. If I take the magnitude of that, that's 9 feet. The symbols here, the absolute magnitude, basically all I'm looking at is how big is my vector. I'm not caring what direction it is, so that's 9 feet to the east. Okay. So if you remember, we had vector A was 6 feet to the east, and vector B was 3 feet east. So what would happen if I had vector C? Let's say that vector C is going to be 3 feet to the west. Okay, now look at that, and I say, now wait a minute, what does this mean? 3 feet to the east, 3 feet to the west. What's the difference here? Well, what if I had vector B plus vector C? Okay, so vector B plus vector C. Well, that would be going 3 feet to the east, then 3 feet to the west. It gets you back to the starting point. So B plus C gets you nowhere, so we call that the null vector. So the null vector would be basically 0. Well, we also know that b minus b would also be 0. So that would mean that minus b equals c. Now, what's the difference in vector b and c? The only difference is direction. Vector c is opposite the direction of vector b. So this gives us an idea of what do we mean by negative vector. So what is negative 6 feet east? Well, if that way is east, negative is that direction. So what's negative 6 feet east? That's the same as 6 feet to the west. Okay, so I could say that I could have vector A, and vector A is 6 feet to the east. Okay, negative A is going to be 6 feet to the west. Okay, and so that means that it's just going to be opposite. Okay, now again, the magnitude of negative A is simply 6 feet. It doesn't worry about direction at all. Okay, let's go back here. We got the idea of what subtracting a vector would be, because what would happen if I had vector A, and vector A was 6 feet to the east, and vector, what do we own, D, is going to be 4 feet to the east. Now, obviously, A plus D is going to be 10 feet to the east. Okay, what would A minus D be? Well, you draw the thing out. Vector A is 6 feet to the east. Vector D is 4 feet to the east, but I'm not adding it, I'm subtracting it. So that means I go back in the other direction. Okay, so that's minus D. So the result is going to be 6 feet to the east. Okay, so what would D minus A be? D minus A, well, that's going to be, D is 4 feet to the east, A is 6 feet to the east, so A would be 6 feet to the east, except I'm going the other direction, negative. So negative A is like that. So D minus A is going to be 4 feet east minus 6 feet east. So what is that? That's negative 2 feet east. Well, what is negative 2 feet east? That is 2 feet to the west. All right, so this kind of gives us an idea of how these collinear vectors add. Now let me point out one other interesting thing here. We did A plus B. Remember, A was 6 feet east, and B was 3 feet east. So that was 9 feet to the east. But B plus A was also 9 feet to the east. So what does that tell us? It tells us that A plus B equals B plus A. In other words, the commutative law of addition holds for these vectors. And this is always going to be true, that the commutative law holds for addition. Now, we are going to discover later on this semester that when you multiply vectors like this, they are not equal if you put them in the other direction. So it's going to be, the commutative law does not hold for multiplication, but it does hold for addition. And so that's going to be an important point for us. Okay, so just hold on to the idea. Later we'll be talking about multiplication. Right now we're just talking about addition. So now you have an idea how we do collinear vectors. So the next step would be what happens if they are in different directions.